Yeah.
Yeah, hello, good morning, everyone. So, welcome to our first session on galaxy morphology. Uh, as we have seen, our group is pretty large and it's an assortment of people. Many are starting for the first time, they are novices, and there are some who are more experienced. So, what we plan to do is, till the time everyone comes up to the same level, we will do a little bit of basics first, and then we would expect our senior people who already have knowledge, learned it here in our workshop, or they've learned otherwise. There are many of you have used Galfit. They can troubleshoot, mentor the others. Okay. So, and don't feel intimidated if you are having problems initially. Don't worry about it because it's a common thing. And the more mistakes you make initially, the better it's for you in future, because then you would know how to troubleshoot and go ahead. So basically, what are we going to do? Yeah, galaxy morphology, like we all know, galaxies come in a variety of shapes. Their morphologies vary. Okay. So let me let's do a fast recap of. Can you hear me, all of you?
Yes, sir.
Yeah. So if you recall, see, our understanding of what galaxies are, it's not very old. Only in 1920s, till 1920s, we did not know whether Milky Way was the only galaxy in the world, in the universe, or whether there were many other galaxies. So there's that famous Shapley-Curtis debate, which was settled in 1920s, where Shapley believed that Milky Way was the only galaxy, while Curtis thought there were many other galaxies. And then observations of Hubble and Hasan, they showed that they could measure the distance to Andromeda galaxy. They could resolve stars in Andromeda. At that stage, it was called Andromeda Nebula, a nebulous object. And they could find certain Cepheid variables, certain variable stars, which are very good variable stars to measure distances, because we know what are the absolute magnitudes. And when we measure the apparent magnitude from distance modulus, we can find out what is the distance from that from us. So they found some Cepheids in Andromeda Nebula, found the distances, and showed that Andromeda was also a galaxy by itself. It was a clump of lot of stars, and the distances to these stars, this clump was much larger than the believed extent of our Milky Way galaxy. So that established that there are many galaxies. And then they looked at all the nebulous objects and they found a zoo of galaxies, right? And then you have that famous Hubble's tuning fork diagram where you have elliptical galaxies, right? He classified into three categories: ellipticals, spirals, and lenticulars. Spirals were broken up into two categories: normal spirals and barred spirals. Barred spirals, right? And you have the famous Hubble tuning fork diagram where you have your um, E0 is circular, E1 is slightly elliptical, and so on till E7. And then you have the lenticulars here. You have the lenticulars here, SOs. And then you have the two branches where you have spirals, where initially you have a large bulge at the center. And as you proceed ahead, you get the bulges at the center become smaller and smaller. Right, and spiral arms open up, right, and then you have the barred spirals, and the arms becomes more open, the nucleus becomes smaller, and so on. Okay, so this was a very simplified scheme of arranging them. These are your SA, SB, and SC, and you have SB A, SB B, and SBC barred spirals, right? And somehow people uh, started believing that this is how they evolved, right? So, but the important thing which initially people thought was these galaxies, these are very far from each other, and there was this island universe concept. They were island universes, and they are basically unevolving. They were not evolving, right? They looked very fixed in space, and it appeared as though they are not changing at all, because during the lifetimes of humans or even generations of humans, the shapes don't seem to change, because these are massive structures extending over 100,000 light years, could be the visible uh, diameter of a Milky Way kind of a galaxy. Others are still larger. And this is as the visible diameter. Otherwise, they could be still larger. But today we realize that our galaxies are interacting. These are dynamical systems, and these are constantly changing in time, right? So galaxies are no more unevolving. They are actually evolving, and we do not perceive it during our lifetimes, but over millions and billions of years, they change the sizes and the shapes. Okay, so what we understand, yeah. So earlier people thought probably ellipticals are formed, and because of their rotation, they start bulging on the equatorial plane, and they become more and more elliptical. And then a disk appears, you have a bulge and a featureless disk, which gives you these lenticulars. And then due to perturbations and other things, the spiral arms appear and they become spirals. So people thought that this is how they get transformed. But then a lot of n-body simulations, which very meaningful, very good ones, which came up in, they started in 1950s onwards, but in 1970s, there were very good simulations done by Toomre and Toomre, which showed that ellipticals can be formed from merger of spiral galaxies. So the spirals can merge and to form ellipticals, right? So the whole scenario appeared to get reversed. It was not necessarily this, but there was a processes which could lead from spirals to ellipticals. Okay, one thing which we need to realize now is what do we mean by morphology of a galaxy? Morphology is what the galaxy appears to be, right? But what it appears to be, it is wavelength dependent, and it is a constantly changing scene. And what it appears to be, this morphology. So one thing is in which wavelength are you observing? It may look like an elliptical galaxy, or you may see it as you may see dust in it, and you'll see uh, disks in it sitting inside and other things. So morphology, and then another thing which we realize is the the velocities of stars, the star trails. These are the ones which also constitute to the morphology of a galaxy. If stars have all kinds of tumbling orbits, like that's what was observed in elliptical galaxies, that they have a lot of velocities in all directions. It's something like it's a churned up, yeah. So the velocities are all in different directions, and you have the whole elliptical galaxy. While in spirals, you have the disk, and the disk, the motion of stars is organized in a circular form. And right, so if you look at a spiral galaxy too, you have essentially three components. If you look at our Milky Way also, we have the disk, we have the bulge, and we have a halo. We have a big halo in which it is sitting. Okay, so we have these three components. And yeah, one more thing about morphology is much also depends from where we are looking at the galaxy. We are fixed in space, and these galaxies are oriented in all random ways, right? So you can see on an object face on, you can see it edge on, right? So suppose, for example, this thing, if you look at it like that, you are looking at it as a burger, while if you are looking at it straight down, you are looking at it like a circular one. Okay, so from what angle and what is your inclination of it makes it look uh, more and more elliptical, or right? So this is looking circular, but the circle, if I am looking at it at an angle, it becomes elliptical. The ratio of the major, the minor axis keeps looking different, and you may think it is more and more elliptical, right? Till the time you see it as an edge. Okay, so this is and we are bound by technology and time. We cannot travel and get another look at these objects. So we are just looking at some fixed position. Even if we change our position while traveling around the sun, it is nothing compared to the distances of these objects. So at what angle are we seeing? We have to make out, and from there you have to make an assessment of what probably it is. Okay. So now, if coming back to our Milky Way, we have this bulge, you have the disk and the halo. The disk has a lot of gas in it, and gas leads to star formation. That's the raw material from which stars are formed. And young stars are hot and bright. And once you have this star formation going on in the disk, then the disk starts overshining, and you see it mostly as a spiral galaxy. Okay, and suppose the bulge of a galaxy is large, right? It's of our galaxy or any galaxy, the bulge becomes larger and larger, and the disk becomes not prominent, or you can't see the spiral arms. You may see it as a lenticular, or if this bulge is extremely big and large, then and you are unable to see the disk, or if the gas in the galaxy has been churned and redistributed and not sitting in the equatorial plane, you will see it as an elliptical galaxy. So what essentially happens, uh, which we realize now, is that an elliptical galaxy can over time start appearing like a lenticular one or a spiral one. A spiral galaxy is barred. A barred spiral galaxy, over time, the bar could break up and it can become a normal spiral, or the bars can form. This is basically, again, the bars are nothing but the um, uh, stellar paths, motion, which gives you the bar. So these bars are transient features. Everything in nature, everything about galaxies is transient. And barred spirals become spirals, spirals can become barred, spirals merge to become ellipticals, and ellipticals can get transformed to form spirals and so on. So it's an ongoing process. And what we see as a galaxy at a certain time is just a snapshot of what we are seeing. Okay, so yeah, and one more thing which we need to see is if you take an image, if you take an image of a galaxy, uh, it may appear to be say a very smooth elliptical galaxy, yeah, or a circular galaxy, or yeah, you may not see other features in it. So in this project, we are trying to study the shapes, the morphology of galaxies, uh, and try to, from morphology, what is our interest? Why do we want to study? Because the morphology or the shape of the galaxy gives you some kind of an insight into how the galaxy has been formed, its past history, what has happened to it, is that it looks as it is today, and also probably predict what it could look like later, or at least let's not go ahead and say what could it look like in future, but at least from looking at the morphology of the galaxy, we'll be in a position to understand uh, what has gone into making it, right? So there are various tools which are used to study the uh, finer features in an elliptical galaxy. One method is you can make contours, do contours of the galaxy, that is right. You try to fit isophores, connect all regions which have the same intensity by a closed, by a curve, and it shows you what how the light distribution is falling. So sometimes you will see that these are perfectly nested contours, and they're all ellipticals. The one sitting inside is smaller ellipse, and they sit beautifully. There are times when you see that these contours, they get twisted. You see that there is a twist in the uh, contour. Here you are seeing it as ellipticals where major axis is in this direction, and here you are seeing the major axis is going elsewhere. Sometimes you see that the contours are boxy in nature, right? They have a boxy features, or the contours themselves, they show some kind of a features like spiral arms and so on. Sometimes you see that they are two brighter clumps sitting here, and then you have and so on. So by looking at these contours, you can see, you can infer from say this figure that this could be a merger remnant. Two galaxies have merged, and you have two cores of two galaxies sitting in the center. That's why there are a lot of stars right here, a lot of brightness coming in, not from one central region, but from two different points. And so this is a merger one. Okay. Uh, in the previous session also we looked at certain things, and we looked at yes, uh, we were talking about Cercic index and other things. We'll come to this too. And it'll make more sense when we start using one tool called GalFit. Yeah, GalFit. It fits galaxy models to your images. So GalFit is a good tool to study morphology of galaxies, and you can download this from net and run it, right? So we have discussed it, but again I can show it for the interest of certain people who have not attended earlier. And this is what you'll have to do. You'll have to download this GalFit. Yeah, it is obviously a free software, and preferably, and in fact it will run only either on a Linux or a Unix system, and in Mac, in your Apple on Mac. In Windows, you can download one Sigwin and create a environment, Linux-like environment, and do it there. But usually it makes your system pretty sluggish. I'll show you this Sigwin. Yeah, I hope you can see my screen. And somewhere here, I'm sitting here. Yeah. So, you logged in somewhere else? You've been signed out because you are currently on another device.
This one is, I don't log inside it. I think this one is there.
Yeah, but I am talking here and.
I will sign up.
Okay. Can you hear me?
Yes,
Hello.
sir.
Yes, sir. Yes, sir.
Somehow it's showing me I've
I've
signed out.
come up.
Okay. Yeah, so see, this is a Sigwin. Yeah, and here you exactly have this Linux-like prompt, and you can do things here, installation running. You can, it's essentially running Linux in your system. Yeah, so if your system is good enough, then this may work fine. Otherwise, it makes it a bit sluggish. Okay, so here it is. Yeah. Right. So now go to my Linux and my screen. And yeah, so you have to go to some. I'm running this Linux Mint here, but Mint is same as Debian Ubuntu. Yeah, Debian is one of the distros for Linux, and you have Red Hat, you have Debian, you have Matrix, various ones, and uh, Debian has a very popular one which is called Ubuntu, and Ubuntu Mint is a slimmer version of the same thing. So you just have to search for Galfit, download, and it will take you to Galfit homepage, Carnegie Institute for Sciences, and this is your Galfit. And right on the web page, you can see what basically it does. See, you see on the left hand side, the image, the science image of some object. These are many galaxies, a cluster of galaxies. One in the center is an image which has been created using Galfit. It's a model image. And one on the right hand side, you have subtracted the image, model image which you have made from the actual one. And so to the right hand side, what you have is a residual. Okay, so how do you subtract these things? What do you do? Yeah, this is. Yeah. And when you get a almost clean image here, see, we are just seeing certain bumps in the residual one, but mostly it's clean. So what it essentially is indicating are that these models which we have put are pretty good. Maybe the one on this right hand side where you can see my cursor moving, this is leaving some kind of a residue here. So the model which it created for this object is not perfect, and you are seeing some features. There's an animation below, colored one, which it's changing as time progressing, right? So one is this is the actual image, this is the model, and then this is the subtracted one, and you are seeing certain features there, right? So many a times when you see that an object appears to be a neat and clean spiral galaxy, elliptical galaxy, or whatever, when you fit these things, you realize and subtract, you will get some kind of a, you can see features and things. Okay, so scrolling down on this page further down, you see this is the region from where you can download Red Hat Enterprise 64, Debian Ubuntu 32, Mac OS X Mavericks, pre-Mavericks, and Debian Ubuntu 64. So depending on what your whether it's a Red Hat or Debian, whether it's a 32-bit or a 64-bit, you can download whichever you need. Okay, and I'm sure you'll know how to find uh, which Ubuntu or Red Hat you are running. Okay, so you can open a terminal and you can check up your version and you will know. So like I know I'm running 64-bit one. So I click on this and it prompts you to save the file. Either open it with something or save the file. I will say, okay, save the file, and I will decide where to do it. Okay, so I will say on the desktop, I'm saving this file. Okay, so Here it shows, and it shows that it has been downloaded. Okay, so it is sitting somewhere. This is the file, and to, to avoid creating a mess on my system, I will create a folder here, and I'll say session September. Okay, and I'll move this here, and this is my zipped tar file. Okay, so I can open a terminal, or you can double click it and untar it and all that, or you can go to your desktop and session. This session is with the capital S. Session here, and you notice I have a GZ file here, so I will unzip it here, and so there, either you can right click it and you can just pull it out. Yeah, it is, you can unzip it like that, but unzip galfit.tar, and it has created a, a tar file. Yeah, and yeah, so it is, when I dragged and dropped it, it gave me what I would have got with all these other two steps. So see, yeah, so now I have a tar file, and I untar it, tar xvf, and I work galfit.distar, and it has created a file here. So let me show what this has. It has the tar file, which you can now get rid of if you wish, and yeah, or you can keep it in some location where you, in the download or somewhere if you need it later. Okay, so you notice I just have a galfit file, and when you do an ls minus l long listing, it will show you the file permissions of this file. And in these new versions of Ubuntu, executable files are showing up as green. So already the file permission is to execute, read, write, execute, right? For the owner, read and execute for the group, and read, execute for others. So execute permissions are there. If execute permissions don't appear, then you do change mode and plus execute and give the name of the file, galfit, right? So what I'm doing now is useless because it already has an execute permission. So yeah, so I have this file, and to run this file, I need some input file. So if I just, in Linux, when you say dot, when you specify dot, suppose I try to run this galfit, this is a executable file. When I'm trying to run this file, it says command not found, because this location where your galfit executable file is sitting, it is not given in our path, in our path variable. Locations /home Najam Anaconda environments IRAF bin home Najam Anaconda this all these paths are there. So any executable file sitting in any of these directories which are listed here, they will run the moment I run it. For example, if I say Conda, it will run because it's already in this path. home Rajam Anaconda, but this particular location is not there. Either I have to set it up in my path, but it's an unsafe thing to do. A better way of running it is you say dot slash. So dot indicates this working directory where I am and run from here. So when I say dot galfit, uh, it is running all this. It's fine. It's saying galfit version 3.0.5, April 23rd, 2030. Enter template file name. It requires some input file in it. Okay. So in short, we are not yet ready to execute this program. So what we shall do is we will take, we need some file, feed me galfit parameters. What do you want to run the galfit by? You require a feed me file, an input file. Okay, so on this page, everything is available for you to start off with. And you will notice that here you have an example tar file. Okay, so you click that, and again we say save file, and I will save it this time in my desktop, and this sessions where we are doing, I'll go and save it in that location and see the download is done, and this is the file. So I will untar it. Unzip it and untar it. It is extract, verify, and post. Right? So this is untarring it. And as you see here, it has created a folder called Galfit example. Right? This is a tar file. Again, we can move it away somewhere where to put it. We have this Galfit example, a folder, and in this you have some files in it. Okay, and what do you have here? There is a copyright thing, example constraints file, galfit.pl, galfit.cl, updates, etc., etc. And an example input file. If you open it, it will show you an example input file. Okay. And then README PDF. You look at this README. These READMEs are always good. Make it a habit of reading these READMEs. It will tell you how to install, how to run, what are the key things, and so on. So this README is the Galfit's user manual, and this is where you have to learn things from and do it. Okay, so we'll come to this paper a little bit later. And in fact, I will, yeah, so this examples, it is this, there is yet another subfolder called examples. And in this, you have some files. One is gal.fits, galfit feedme, psf fits, and readme. So always nose around into these readme files, and they tell you what to do. So this readme file says to run this example, simply type galfit.feedme, right? So it wants you to run this thing, okay? But obviously something which he didn't write, which he expects you to know is that this file, which file? This galfit executable file, it should be sitting somewhere where that feedme file is, or you'll have to give the whole path to that location. So what I will do is I'll just make a copy of this and go and paste it here, right? You do it in the GUI, or you do it through this command line. So presently I am in sessions this, and I will get into Galfit examples. And in Galfit examples, there is the examples with capital. See, Linux is case sensitive. Small e and capital E example written with caps and with small are two different things. And here we are. So let me clear this thing and show you that we have in this directory Galfit feed me, Galfit fits, PSF and readme. Okay. So what are these fits? Fits is a way of transporting images. There is a format which astronomers are using a lot these days. It's by these days I mean for the past maybe 20 years. It is flexible image transport system, FITS files. So these FITS files, they are not just images, but they also carry with the images some more information. Information about the image which has been taken, in the sense of when was it taken, what was the exposure time, um, are there any bad pixels in it, and there are a variety of things which are there, which you will see as you proceed. So these FITS files are a way of backing up images and transporting it across to people with a lot of information other than only the image. Okay. So how do we see these FITS files? Old classical way in which we used to do earlier was use something called IRAF. But now IRAF is not being supported and you can't find it and download and install. While in some versions of Ubuntu, I think 16.04 and so on, you can go and install it from the package manager. Right? For example, in this Mint, I could manage to do it. And there are a couple of things. For example, DS9 is a DS9. It allows you to view images. Yeah, it's a SAO image thing in which you can see these images. Okay. And similarly, you have this IRAF. I'll just show you since some of you have IRAF running and working. So in IRAF, this is your IRAF prompt, and I'll have to go to the location where all these things are sitting, session, and then in Galfit example, and here. And if I do a display, and give the name of that file. See, that file is gal.fits. So when I say display, give the gal.fits, and I say in which frame I should put it, it will show you the image. Yeah, it is showing you the image of this file. Okay, and similarly, I can display in my second frame the PSF, the point spread function, which came to us this time with the examples tar file. And I will see this PSF point spread function in my second frame, right? So the see it's showing you how your it is showing you the point spread function for that image, right? So how do we get these point spread functions and other things? We will come further into it. As of now, what you need to do is that when you untar the examples thing, it comes to you directly. Okay, so this is my IRAF session. I will open one more terminal and I will go to that location where my session, where we are running this GalFit and example thing, right? And now we have in this location, this GalFit file, the feedme galfit.feedme file, and you have the image file, PSF file, and so on. And this README file we have already seen, which says to run it. Yeah, so we'll run it now with /galfit, and I'll give the name of that feedme file, right? So if you want to have a look at what the feedme file is, it is a text file, and this is what it looks like. It tells you input image. It's a fits file, right? So here you have to give the name of the image file. Whatever the name you have sitting here, you have to give. For in this case, the name of the image is gal.fits. So that's what is written here. Then output image block is im-block fits. You can change it to anything. You can call it out.fits, and then the output image it will create will be called out.fits. Okay, I leave it as it is. And sigma image name, it says there is no sigma image. If we had, we will give the name of that. It's none here. And if you need to read the instructions on the GalFit page, it will tell you what the sigma image thing is and how from version 3 it's not much required. And then you have this PSF fits file and all these things. Okay. Further, what it's showing is, it is telling you what are the parameters which you want to fit the file. So there are different types of functions which are there. Basically, what do we mean by this is this? See, if you look at a galaxy, you notice that the light distribution goes by a certain function. Generally, it's very bright at the center, and as you go on the edges, the intensity falls. And how it falls varies for different types of galaxies. For ellipticals, they fall by a certain amount. For disk galaxies, exponential disk, they fall exponentially. And there's a different, and over the years, people have given different models which show how light distribution falls in a model. So you have this Luca profile, Cercic profile, exponential disk, devacular, King's profile, PS, Gaussian, Moffat. There are various power, Cercic, Sky, and isoport, right? So as of now, we will look at the ones which are interesting is this devacular profile, right? And this Cercic. So Cercic index, in fact, Cercic index 4 gives you the devacular profile. Cercic index gives you an exponential disk profile, 1, if you take it as 1, and it will show you how the light is falling, right? So you choose the what kind of function we are trying to fit, and it creates you a model image. And in this, you have diskiness, CO, diskiness, boxiness, right? There's about the CO component and other things. From version 2 to 3, they have changed a little bit. But right here, you will see all these things. So Cercic, so we are in this sample file which came with our tar ball, it is trying to fit two components. Object one is you are fitting a Sursic profile. Yeah, this is the object name is Sursic. If you change it to exponential disk, you should write exponential disk here. If you want divacular, you write divacular, right? So in this case, we are taking Sursic 1. This 48.518051 point, this is the position XY. It's a center. Okay. Then integrated magnitude is 20 at the magnitude scale. The half-light radius at which the light of the galaxy falls by half the amount, lies half of the amount of galaxies which lies within it is called the half-light radius. And then you have the Sursic index. Here he is giving 4.24, right? And this B by A, major axis by minor axis ratio is 0.75. Position angle is -60. And output option, if you say 0, then it creates a residual. If you put 1, it doesn't subtract it. Okay, so if you take if you put 1 here, then it will just create output image. But if you put a 0, it will subtract it and also give it. Similarly, you have the object 2 here, and this is your fitting. So there are two components. One is the Sursic, other one is the sky. Okay, and this is sky, and then sky background is 1.3, and okay. And how do you get these values? We will come to that as we slightly proceed ahead. So there is something called source extractor, or from the site where you get these files for certain images, you can get these source extractor files, which give you how to get these parameters. Or you can visually see this object, plot it in this, and you can see what they look like, right? What is the major axis, minor axis? By visual inspection, you can make a rough estimate of what these things are and try to, right? So physically, see the center, when I'm moving my cursor, it is giving 42, 47, and so on, right? So that is giving you the center. I'm missing by some pixel. Okay. Right. So now let us not wait further. We will run this. We are running this .galfit. With this galfit dot feed me. Yeah, whatever name, the name of the input parameter file is, that's what you give, right? So galfit feed me, and it is running it. So you are doing, yeah, it's done an iterative one, and it has done a fit, and it says the fit summary is now being saved in fit.log. Now you will notice that a fit.log has been created. Okay, and you can also notice that this in-block fits has been created. This in-block fits is the residual one which it did, and this is the log file. So if you look at the log file, it will show you with what parameters it has fit. It says the input image was gal.fits. The parameter file was galfit.feedme. The restart file. Now, see, it has created, if you notice, there's a galfit.01 it has created. So if you want to rerun now with the new parameters which is fit, then this you can use it as a restart file. And then it will create the galfit.03 or whatever. And the output image file is this inblock.fits. Okay, now it is giving you certain more things, which says Cersei 46.53, 48.28, then 22.98, this, and right? So what do we understand by all this? We can go back to your Galfit feed me file. Yeah, so you notice this 46.53, 48.23 is the center which the Galfit has found. What was given by us in our feed me file was 48.5 and 51.28, but it found the center better, and Galfit is suggesting the center to be 46.53, 48.48 rather than what was given. Okay. Then the uh, second thing is the integrated magnitude 20.089 was what was given in the feed me file. But here it is giving you 22.98. This is what it is recalculated. And similarly, so all these, if you notice, all these numbers, 7, 8, are these numbers, right? First two in bracket are the 1, which gives you the position of XY. Then this, and the Cersei index, the fourth one, half-light radius was 5.14. Here it gave you, what did it come as 1, 2? Integrated magnitude is 22. Then half-light is 5.1, is 2 point this. Cersei index is 4.42. That was the one which we had, but it is calculated as 4.01 and so forth. Okay. Another thing, similarly for sky component, it has given you all this. Okay, and then look at this, the sky square by 1.469. So your chi-square value, if it is close to 1, then it is showing you, it is giving you that it's a good fit. Okay. And now when you rerun it with this, you will find another, you may improve on this, or if you don't improve your chi-square by nu, right, it will remain this. That's by standard deviation, chi-square by standard deviation. So if both are the same, then you will get 1, which will show you that the fit is good. Otherwise, but whatever fit, it tells you it's the fit with this kind of errors. This is the, okay. Now, if I would like to see the residual image, which it has created, again, I can I say display, and what is that thing, im block dot fits, and I will show it in frame 3 because 1 has alpha, 2 has the PSF, and in 3, but it is saying that must specify fits extension. So this im block seems to be like a queue. It is not showing it. So what I can do is, yeah, so I will display fits, and I will, the second block, as I know, has the image in it. Okay, so this is the thing which it has found. Okay, so I can make them blink. Yeah, so I can, single one I can see. So this is the image. And this is the session में हूँ मैं अभी कॉल करता हूँ. Hello. Yeah. So this is it. And suppose you are having problems using this IRAP installing and running it. All this can be done through AstroPy. Python has kind of replaced IRAP and all. In fact, IRAP went into IRAP first, and that's what is running here. And then the Python and AstroPy has become such a powerful tool that you can do all this. You can handle your fits file and other things directly through Python. Okay. So yeah. So otherwise, what do is there's something called arithmetic, where you can do e power, and I say arith, right? I'm changing the, and I will give you the operand one. In this is what is the name of the file. What I'm trying to show is how subtracting this gal fit from this in block, and we'll find some other residue. So if I say operand one is gal dot fits, and the operation is minus, and here I am operand two is in block fits dot two. Okay, and the resultant file name I'm calling it result dot fits, and when I say run the command, you see it has created one residue.fits here, which again I will display this address dot fits in the fifth frame. Spelling S didn't come. Display address dot fits in same frame 5. Okay, so see, this is my subtracting. When I am subtracting the image from the model, this is the residue, and you can see that it seems to be a pretty good clean duct. Only some object has remained here. Okay. Yeah, so we have this image subtracted and so on. Okay. So this is how this goes. And going back to where we started, going to Galpit page. There is this paper on new Galpit version 3. This is the original paper on Galpit, Peng et al. 2002, and in 2000 there is this new one. You should have a look at it, and you can download it from archives and read it. Okay, so and then you have all these instructions on using GalFit, and all these things are bare bones, all possible functions, various things. Okay, so let me stop for a moment now. And if there are any questions, then let us see. Could you all understand what was happening?
Yes, sir.
Hello? Could you follow me, all of you?
Yes, sir, we could follow you.
Yeah. So now the thing is, what is the whole purpose of doing these things of GalFit? So once we saw that log file, once it is fit and it is giving you the output log file, it tells you those parameters which it has fit, right? So one important parameter, just to start off with, is you can say find out what is the Search index. And Search index, if it is say greater than 2, then the bulge type. So we are fitting different components, and when the bulge which you are fitting, if the Search index is greater than 2, then we call that this is classical bulge. And classical bulges are those which have been created by basically major mergers. When two big galaxies, by major mergers we mean two equal mass galaxies, big galaxies, come and interact and merge. Like Milky Way galaxy and Andromeda galaxy will have a merger after 300 million years or so. These are major mergers. But if it is less than 1, then what we see, if it is less than 2, then we call them pseudo bulges, the bulge, right? So we have picked the specific parameter for pseudo bulge, which it has iterated and found. If it is less than 1, then we say that it is a pseudo bulge. And pseudo bulges are formed by secular evolution, right? So it kind of tells us whether that bulge, what is the bulge type, whether it is it's a remnant of two mergers, or whether it is a small mergers have taken place and over time it has evolved and secularly evolved into this, right? So right from Search index we can get what type of it is, and it gives you an indication how that bulge is informed. Similarly, you can get the bulge parameters, you can get the disk parameters, then you can study the bulge to disk ratios, and again you can plot them on different uh, relationship diagrams, scaling diagrams which we have, which we shall see, Cormandy diagram and other things, and then again get an idea of whether these are merger remnants or major merger remnants or so on and so forth, right? So for some people there who have already done GalFit, maybe this session was not much of use, but there are many with us who have just started, and they have to download these things, run them and see if they are having problems and issues. I have certain versions of Ubuntu, you can directly install it through your package manager. Earlier, we had to go to this website, NOAO site, download these zip files, untar it, and unpack it in certain way and get it running. But that thing is now packed up. And in fact, people are slowly moving to AstroPi. So we can also have some sessions on AstroPi, how to handle these. We already had, I think, earlier, but we will again probably do it in more detail. Anyway, for GalFit, we don't need too much of AstroPi. We just need some basic things. How to access these fits files, how to view them, how to get the header information from them, how to subtract two frames from each other, how to save the residues in something else, And yeah, there's not much of it. So you don't have to know much of coding for that. And so is there anything specific somebody wants to ask? They can ask, or else we can stop for today and we can meet again uh, next weekend or during the week, whatever suits you all. Let's discuss it in the WhatsApp group. And in the meantime, try to run it, install it, get into trouble, ask in our group, and some of us will handle it. Like we have Sukhvinder Kaur here, she is an experienced person. She knows how to run these things. Similarly, I don't know whether Mrinalini is here. Yes, Sukhvinder, you can help, right? Mrinalini is here. Abhishek is also our senior person. Teja is new. Gitanjali is experienced, right? So, in fact, as the time progresses, I would expect you all to know more on this than I know, because you are the ones who will actually get your hands dirty and run this. And we will only monitor and we'll see how we can use the information which comes to make astrophysical sense and how can it be used, right? And you have to get used to seeing those key papers, manuals, and run them. You have to learn how to actually get your hands dirty and do it, right? And as time progresses, there are some of you who are senior, like Mrinalini is running Tiny Tim, and she has progressed much. Yeah, there are some issues. They will tackle those also. And right, so either separately you can write at what level of difficulty you are in, and for some more advanced people in the group, maybe we can also have separate sessions. Otherwise, the young ones, there are some school enthusiasts also, and we should not make them intimidated. Yeah. So we can have separate sessions for those who are novices. And those who are starting now should realize that everybody went through this at some stage. Everyone at some stage had problems running a particular command and running into trouble. Okay. So you have to try, and that's the only way. Gitanjali, you are a senior. You want to say something?
No, sir. Thank you. I mean, I'm also new to using Galfit.
Okay. But you have good experience in astrophysics, astronomy.
Yeah.
So even Sukhvinder, you have done. Yes.
Sir, I have done a little bit, but I'm not very proficient with it. I took help of Manali also. I told her that I will again approach her, but now you are available, so we'll discuss with you. So I have done a little bit, yeah.
Yeah. So we can meet separately too. Those who have already progressed, and then you can start mentoring the younger ones, and we can go ahead. Okay.
Yes, I will try.
The new ones who have joined with us this for the first time or so, are there any questions or suggestions, comments? Tamima, Suman, Sharon, Teja, Rama, Vikrama.
Not really, sir. Looking forward to learn a lot.
Yeah.
Thank you, sir.
Yeah. Okay, so then we'll meet next week. Okay. Shall we stop for now?
Okay, thank you, sir. So maybe we'll meet next week at the same time. I think that will be better, so that anyone has problem, then we can discuss.
That's right. And if there are any problems in between, you can write and we'll see whether you can troubleshoot.
Yeah, definitely.